A queue is a collection that returns elements to your program in a special way. You add elements to the queue in the normal way. The queue collection keeps them in some kind of predefined order, and when one is returned to you, it is also removed from the collection. All queues have at least two methods to insert a new element onto the end of the queue. The add method inserts the element and throws an exception if it can't. The offer method does the same thing, but instead of throwing an exception, it returns an error code. At least two methods can be used to return an element from the head of the queue. The remove method throws an exception if there is an error, and the poll method returns an error code. Both of these are what is known as destructive readers. That is, they do two things. They return the element and delete it from the collection. These two methods are non-destructive reads. They return the next element, but leave it in the queue. The queue classes fall into two categories. There are some that are designed specifically to work well with multiple threads, and I'll be describing those in a future lesson. But there are three that are not thread safe, but work just fine in a single-threaded environment. The priority queue is probably the simplest of all queues. The elements are sorted by either their internal comparison method or by a comparator that you provide on the constructor. It will accept duplicate key values for the sorting. It returns elements from the queue in sorted order, but the iterator does not return them in order. The ArrayDQ class, in addition to the usual methods for a queue, also can be iterated and has a number of methods making it possible for you to access the elements in about any order you'd like. Some of the read methods also delete elements from the collection and some do not. In particular, it has a push method and a pop method, so it can be used as a LIFO buffer, last in, first out. Such a buffer is also known as a stack. This collection is maintained as a double-ended linked list internally. You can add to and remove from either end. You can even add elements to a point in the middle. It also has push and pop methods, so it can be used as a stack. This is an example of the use of a priority queue. The elements in a priority queue are sorted in the same way we saw in earlier example. The elements either implement the comparable interface or you can provide a comparator on the constructor. Also, with the priority queue, you can specify the initial capacity on the constructor. It doesn't matter because the capacity will expand automatically as necessary, but you can increase the efficiency if you happen to know how many elements you are going to put in the object. In this example, the priority queue is constructed to hold strings and they're not added in any particular order. All this is just as we've seen before. The difference is in how the strings are retrieved from the collection. This while loop executes as long as there are elements remaining in the queue. The poll method is used to read the elements. This method returns the head, the first member of the queue, and also removes it from the queue. Each string element is printed as it's retrieved. The result is that the strings are printed in queue order, and the queue is left empty. Here's how it works. As you can see, the elements are returned to the program in sorted order. So in spite of its name, this is not really a queue. It's a sorted collection with a destructive read. This is an example of using an ArrayDQ collection. This class can be used as a queue or as a push-down stack. It does not sort the elements. The order they come out depends on the order in which they go in. If you want to use it as a stack, which is first in, last out, you can use the method push to add the elements and pop to retrieve them. This example uses it as a queue, first in, first out, by using the methods add and poll. The body of this example is exactly like the last one. 6 strings are inserted in no particular order, and the pole method is used to retrieve them until the queue is empty. Here's what it looks like. There you see the result of storing a stream of elements in a FIFO queue. They come back in the same order in which they went in. You can continuously add and remove elements, and the queue will keep them all marching in single file and give them back to you in order. The queue will grow to whatever size is necessary to hold all the elements that you give it. This example uses the linked list collection. It works the same as the previous example. The only difference is the internal implementation. In the previous example, the ArrayDQ used an array for internal storage. In this example, the linked list collection uses a linked list structure to do the same job. It can be used as a queue or as a stack. This example is just like the last one, and it works the same way. The elements come out in the same order they go in. Next up is copying elements from one collection to another and extracting arrays of elements.